Hello, welcome to this instructional video regarding half-wave rectifiers. As we've discussed in the past, half-wave rectifiers basically have, at the simplest level, two components. One, they have a transformer that changes the AC voltage input from one level to another. Now, in almost all cases, transformer is going to step the voltage down. For example, in the United States, the most common voltage to the input of a transformer is 120 volts. The secondary voltage could be almost anything. But let's just say, for example, that the secondary voltage is 12 volts. That's the secondary voltage. Then we can look and see what kind of output we'd have. So the secondary output would look like this, just like the input, with this being kind of the zero line through here. So let's determine the peak voltage on the secondary if the secondary voltage is 12 volts. Now this is the RMS, root mean square, or the effective voltage coming out of the secondary of the transformer, which will be the way transformers are rated. Transformers are never rated in terms of its peak voltage, although that can be calculated. So to calculate the V peak, we use this equation here. V peak is equal to our VRMS divided by 0.707. In this case, we have 12 volts. We're going to divide that by 0.707. Now, if we bring up a calculator, we can calculate what that value is. So it's 12 volts divided by 0.707, and that yields us a voltage of 16.97, almost 17 volts. So we'll just round that off to 17 volts. Peak. Okay, so this voltage here now is 17 volts. Now the diode up here will drop about 0.7 volts, leaving the voltage to my, and it will also block this portion right here of our waveform. So the voltage to the load will look like this. And then this part will be level. There'll be blocking during this time. And the voltage peak here will be this voltage here minus 0.7 volts for the diode. Remember, when the diode is conducting, it will drop somewhere between 0.6 and 0.9 volts. The commonly accepted voltage drop across a diode for a silicon diode is 0.7 volts. So that voltage is going to be 17 volts minus 0.7 volts, or 16.3 volts. Now that we know the peak voltage to our load resistor R, we can calculate the DC voltage. Now, DC voltage is going to require a new calculation, DCV. That equation is going to be very simply this. It's going to take the peak voltage to the load, V peak, divided by pi. In this case, 16.3 volts divided by 3.14. Again, we'll bring up our calculator. 16.3 divided by 3.14 is equal to 5.19 volts. Or about 5.2 volts. Again, we're rounding off these numbers and we're estimating the voltage drop across the diode. So we have an AC input of 120 volts, a 12 volts RMS output at the secondary. We have 0.7 of a volt drop across our diode. Our voltage to our load looks like this, V load. Looks like this with a peak value of 16.3 and our DC voltage of 5.2 volts DC. Now, this is often referred to as pulsating DC. Because the voltage is not steady. It rises to a peak value, falls back down to 0, and for half of the waveform, it's actually 0 volts. So you're not getting a lot of DC voltage output. You may wonder, where in the world would you ever use something like this? Sometimes it's used for battery charging, where you're charging up, say, a certain battery voltage. Maybe you had a 15-volt battery or 12-volt battery, and then it would only charge the part where this waveform got over 12 volts. So it's used for just trickle charging, and it's a cheap way of having a power supply that will charge up a battery. Not very effective, but it is sometimes used. Now let's calculate the maximum current to our load and a few other things. So the maximum current to our load, now the load current will look the same as the load voltage. So I, load, is going to look the same way like this, provided that the load is a resistive load and is not reactive. Now what we want to do here is calculate the peak current. So the peak current, I peak, is going to take our peak DC voltage right here. I is equal to V over R, if you'll remember. So it'll be our V peak, which is going to be 16.3 volts, and divided by whatever value our R is. Now we'll assume here that R is equal to 1K ohm. To make our calculations pretty easy, 16.3 volts divided by 1K is going to be 16.3 milliamps peak. Now to understand it, we need to understand that is the peak current right here, 16.3 milliamps. And sometimes that quantity is needed. Our current, or our DC current, IDC, is going to be our average. So we'll use, in this case, same equation, V over R, but we will use 5.2 volts divided by 1K, which is equal to 5.2 milliamps. Now this is my average DC current. Okay, now I hope that helps you understand a little bit about these power supplies. One other thing that we do need to talk about is the diode PIV rating. The PIV rating is the diode's, the amount of voltage the diode will have to block. Well, in this case, since the incoming voltage rises to a peak of 17, it's also blocking this negative 17 volts down here as well. So in this case, the diode, the PIV, peak inverse voltage, or PRV, the peak reverse voltage, both are the same thing, must be greater than 17 volts. Now, in that case, we can use a 1N 4001 diode, which has a PIV rating of 50 volts. So this is a fairly low value, but in some cases, some diodes, for example, LEDs, can't block that much voltage, but a 1N 4001 diode can. And 1N 4001 diodes are also rated for 1 amp, and this is very, very small, 5.2 milliamps DC average current. Hope this answers some of your questions and will help you with your week 1 online assignment.